So now we're going to talk about the area between curves. So in general, how do we find the area between two curves? All right, so I'm going to drop in a sticky. Okay. I'm going to, let's see, make the squares a little bit smaller. And I'm going to do another one of those right here. Okay. So, draw my y-axis and my x-axis. Now, say I've got some function f of x and another function g of x. Excuse me. And now I want to find the area between the curves from maybe this point to this point here. So we'll shade that in. So we want to find the area of this weird looking flagged shape object. Okay. So how do we do this? All right. So area is equal to the integral from, well, the top. Now, typically it's a to b f of x dx, right? But this was whenever we were finding it with respect to area above the x-axis. Now, if you think about it, if we're above the x-axis, then that means that everything is above some h of x function that's equal to 0, right? So technically that distance between f of x and 0 is the top minus the bottom, right? But here it would be the top, which was f of x, minus the bottom, which was 0. So that's where that height comes into play, okay? But now the bottom is no longer the 0, but it's this g of x function. So we need to back it out a little bit. Okay? So when we do this, this is going to be the top minus the bottom function. Okay? And where is our a to b? Well, the a is the most far left endpoint. Okay, so over here. And the b is the most far right endpoint. Okay, that's over here. All right. Now, how do we know what we're integrating with respect to? Is it dx or dy? Well, up to this point, all the problems that we've done have been with respect to dx, so with respect to x. But to show you this, we draw an arbitrary rectangle. So I'm going to draw that arbitrary rectangle. Okay. So when I draw my arbitrary rectangle, I see here that arbitrary rectangle has that height of what we're looking for, the top f of x minus the bottom g of x. Okay, but what about the width? What is that width there? That width on the top and the bottom is the same. That little width is a change in x. So a change in x is a delta x. Okay, so dx is my width there. You can see I'm making dx slices. So I'm doing several little arbitrary rectangles, and I'm literally just, oh, come on now, let me copy it. Okay, and so I'm just adding up all the rectangles that fall into place here. Okay, so the more rectangles I get, the better my approximation is, and I just keep adding them up, adding them up, adding them up, and I make them smaller and smaller, and my delta x's get smaller and smaller. They're going to 0. That's that Riemann sum thing going on that we talked about in Calculus 1. Okay? So this simplifies for this particular arbitrary problem if we have, let me delete these real quick. Okay, so if we have this value right here is x equal to a, and this value right here is x equal to b, right? Then this integral becomes, based off of the information we're given here, the formula is the integral from a to b. So remember, from the left to the right, so we integrate going left to right just like we read, okay, of f of x minus g of x, top minus bottom, delta x. Okay, so that's what we call, when we're finding the area between two curves, we call this version the x easy. Okay, x easy. So that means that it's easy to integrate with respect to x. So x easy, we've got our delta x, all right? So that means when we're making our rectangles, our small width is the delta x part of the rectangle, okay? Now, for the next part, let's do another one, another graph, and I'll have my y-axis, and I'll have my x-axis, and I'm going to have a function that is not a function in terms of x. As you can clearly see here, it does not pass the vertical line test. It fails it because vertical line passes through in more than one spot. And so let's call this function h of y. So a function in terms of y, right? So it passes the function test going this way. All right, so it's a function in terms of y, and then maybe some other function k of x or k of y here, okay? Now, how do I find the area here? And say, I want to know, from here down to here, and I want to know this shaded area right here. Now, we could do this x easy, okay? We could do an integral where we did rectangles, okay? So if I picked out an arbitrary rectangle like this, okay? Now, the thing is, right here, the area would be easy. It would just be the top minus the bottom. Well, what is the top minus the bottom here? The top, maybe this is line y equal to d, and this is line y equal to c down here, right? Okay. So what would the top minus the bottom be here? It would just be top minus bottom, d minus c there. But what happens as the rectangle moves to over here? Okay, Because remember that rectangle moves. Okay, so as we move, all of a sudden, boom, wow, it looks like the bottom is now changing versus the top is still D, but the bottom is now h of y. And then if you go even further, you get to a point where the top and the bottom are both h of y, okay? So what's happening, you would have to break this up into several integrals where the changes occurred. So to give you an example how many integrals you'd have to break this particular problem into to do it in the X-easy version, in the X-easy version, you'd have to split it up here. And I'm just eyeballing this. You'd have to split it up here, and you'd have to split it up here, okay? So you'd have to do 1, 2, 3, 4 integrals to do this in X-easy. Now, X-easy doesn't sound so easy anymore, does it? So what we're going to do, instead of integrating X-easy, we're going to integrate Y-easy. So what does that look like? That looks like this right here, dy instead of dx. How do I get this distance from here to here? Well, how do we tell the distance between 2 points on a number line? Well, you think about a number line, 0, 1, 2, 3, 4. How do you find the distance between the unit 1 to the unit 4? Do I do 1 minus 4 and that distance is negative 3? No. I do the right minus the left. Okay, so I do the right minus left. So what is that? That would be 4 minus 1, which gets you the 3. Sorry, I jumped ahead there in my head. Okay, so I do the right function minus the left function. Okay, so the area here is equal to what? It's the right h of y minus the left k of y. So the right minus the left, and then where am I integrating from? Well, here I did from left to right, okay? From the smallest to the biggest, right? Well, from here, I'm going to do from the smallest to the biggest. What's the smallest? The lowest to the highest, from bottom to top, okay? So I'm going to integrate from bottom to top, all right? And then remember, I'm integrating with respect to y, so that's a delta y, so dy. And whenever I make the connection here, if this solid line here is at y equal to c, and this solid line here is at y equal to d, kind of like in the same way we went from x equal a to x equal b, this area becomes the integral from c to d of the right function, h of y, minus the left function, k of y. And now remember, we're integrating, and these are functions in terms of y. So this is something like, I don't know, y squared minus 2y, right? And then, this one's like minus, I don't know, y cubed plus 1, right? So these are in terms of y, so you would think, yeah, I would integrate with respect to y, okay? So the only thing there is changing is the letter, all right? So if you have a function and it's defined like this, maybe it's best if you take that function right there and you, maybe you work with it to integrate in terms of y instead of trying to solve y equals in terms of x, because you end up not getting that function there. Clearly, this isn't a function in terms of x. So it gets kind of nasty if you start trying to do x easy. So we try to go for the path of least resistance, the easiest way to solve the problem. And so this is y easy. Okay. All right, it's y easy because the function, it's not a function of x. Just like this was not a function of y. Okay. See, if this here, it's a function of y for this one, it's a function of x for this one. That's why we use x easy for the first one and y easy for the next one. Okay. So h and k, these two functions here, are relations, yes, just like f and g are relations, but a function is a special type of relation. So this is a function of x because it passes the vertical line test. This is a function of x because it passes the vertical line test here. This is not a function of x because it clearly fails the vertical line test. This is not a function of x because it fails the vertical line test more than 2 places that it crosses. However, if we look at this function here, this is not a function of y because when I draw a horizontal line, which is the opposite of the vertical, right, it crosses more than once. This is not a function of y, it crosses more than once. But this k of y is a function of y. It only crosses one time with a horizontal line. And this is a function of y, and it crosses one time there. So what do we have? We have function of y here and function of x here. So f and g are functions of x, and k and h are functions of y. Okay? So that's where we have the x easy versus the y easy. So these formulas right here are about as general as you can get. You need to understand these and memorize them. Okay? You need to fully understand what's going on with those two formulas right there. All right, so I hope that this was a good introduction into area between curves. If you understand this video and know how to apply it, then the rest of the videos are kind of pointless to watch, but you might as well watch them so you can actually see this theory in action. Okay, I promise you, practicing through the problems is where you're going to learn it, not just watching a video. All right.